Hi, everybody. Today, I'll quickly walk you through my TAX V3 reinforced learning project. I'll cover the problem, the Q learning algorithm, training and evaluation, what I learned about exploration versus exploitation, parameter tuning, and close with a short discussion. TAX V3 is a classic 5x5 grid world where a taxi must navigate around fixed walls, pick up a passenger from one of four locations, then drop them off at a designated destination. There are 500 discrete states. That is a state that incorporates taxi position, passenger location, and destination. And six actions that include north, south, east, west, pickup, and drop off. Rewards are plus 20 for successful drop off, -1 per step, and -10 for illegal pickups and drop offs. The goal is to learn a policy that completes the ride efficiently. I implemented Q learning, which estimates action value Q S of A using the update. So we have Q S of A equals Q S of A plus alpha, which is the learning rate, how strongly we incorporate new information, plus gamma, which is a discount factor, how much we value future rewards, times max of A prime, Q times Q S of A, S prime of A prime minus Q S of A. So, in simpler terms, right, it means we slightly adjust our estimate of how good an action is based on the reward we just got and what we expect to earn in the future. We act with an E greedy or epsilon greedy policy with the probability that epsilon will choose a random action, explore, otherwise choose the action with the highest Q value, exploit. Epsilon decay over time does favor exploitation later. So the epsilon is the exploration rate. And then when we look at that plus the epsilon decay and epsilon min, we can manage exploration time over training. Now, exploration, this is a high epsilon. This encourages new routes and strategies. It fosters robust behavior in those environments that are very diverse. Where exploitation, this is a low epsilon. It focuses on utilizing the learned Q values to maximize immediate returns. It relies on established knowledge. And then we have, with these two, trade-off dynamics. Fast epsilon decay facilitates quicker convergence, but may trap the algorithm in a local optima, where slower decay promotes thorough exploration, but can hinder early learning. So you can see why these two things are important to try to maximize. So when we're looking at parameter tuning plan, are optimizing the Q learning with strategic parameter adjustments. What we're going to do is first before we do this, we want to make sure that our environment works. So before training, I did run a 10-step random policy rollout. And basically, this simply selected actions at random for a few steps to visualize how the taxi behaves without learning. It did print the grids after each move, showing random movement, penalties for illegal actions, and occasional rewards. So this was to serve as a baseline, an on-trade performance that typically gives a very low reward. In my example, it had about -200 in the reward, and it didn't go to completion. When we talked about defining our Q learning parameters, I did create a Q parameter data class to store hyperparameterizations. So for instance, alpha was the learning rate, gamma discount factor, epsilon exploration rate, the epsilon min and epsilon decay, those both controlled exploration decay. And then I had my epsilon and max steps that defined the training length. And I made a data class, because it made it easier to adjust parameters and run experiments systematically. Now, when I initialized the Q table of size, it was states times action to 0. For every single episode that I ran, I reset the environment, chose actions using that epsilon greedy policy via choose action, and then updated Q values with that formula that I discussed. and gradually the decay epsilon to shift from exploration to exploitation. So the algorithm tracked total reward steps and success rates across episodes. And so training. This was the baseline configuration that I ended up picking for the Q learning. I did test some variants. I ended up with the decay of 0.99 for slower exploration, and I went up to an alpha. I did try 0.2, but in this example, I have an alpha of 0.3. And I did run 10,000 episodes. And so as I was going through here, the agent's performance steadily did improve. Average rewards reached somewhere about 7.4 per episode with 100% success, which was great. And so this did indicate that the agent learned to consistently pick up and drop off passengers online. So when I evaluated the effectiveness and efficiency of the learned taxi policies through key performance indicator, I looked at the average rewards per episode. So we looked at the average step to complete the task, the success rate, the learning curves, and parameters comparison plots. So in the average reward per episode, we noticed that it was noisy, but it did show progress. Here in the average steps to complete the task, the average reward was around about 7.7. The short episode length was around 13, and it had a near perfect success rate, confirming convergence. And here you can see the success rate curve, which shows increased consistency. And we're going to look at this learning curve and the parameter comparisons here shortly. But we did see with the epsilon decay curve how exploration did reduce over time. And then this was a moving averages of 100 and 500 episodes, and it did reveal kind of performance trends that were happening. So the baseline here is the alpha 0.1, epsilon decay that we used was 0.995, and then the gamma is 0.99 for all of these, and the epsilon is up 1 to 0.05 for all of these that we're looking at. And so you can see here with the slower exploration decay, I set that epsilon decay to 0.999. The faster exploration decay, I sent to 0.99. And the higher learning, I sent to 0.3. And if we look here, all achieved 100% success, but average rewards did vary slightly between them. The baseline performed the best, though, when we looked at everything put together. So the experiment did show how learning and exploration rates can affect convergence, speed, and stability here. So the final takeaways here is that Q learning learns an efficient taxi V3 policy with near perfect success after sufficient training. Managing the epsilon decay is crucial, keeping exploring long enough to avoid premature convergence. Tuning alpha, your learning rate, for your stability and speed is needed, and you want to set your gamma high for long-term planning. Always validate with greedy evaluations and visualize both raw and smooth learning. Now, how can we improve the implementation of this algorithm? Well, better exploration schedules, epsilon linear versus exponential decay is a possibility. You could cold restart the epsilon reset. Basically, you can do optimistic initialization. You can do reward shaping and even learning rate schedules. I did read that you could reduce the max bias by doing double Q learning. and even doing eligibility traces could help. So all of this, even trying function approximation, where you take basically tabular to smaller neural networks with careful stability controls. Now, I use Q-learning. So what would I expect with SARSA on this task? And basically, SARSA is an on policy. So it tends to learn values very consistently with the behavior policy. So with epsilon greedy, it often learns slightly safer, less riskier policies in stochastic settings because it expects future epsilon greedy actions. Q-learning is an off policy that evaluates greedy targets and can appear more optimistic. It often learns faster to high returns, but can be less conservative, aka it's more risky. So if I'm looking at on policy and off policy, on policy, SARSA, values align with the current exploratory policy, which can temper risky shortcuts, but sometimes is slow for peak performance. Off policy, like Q learning, which I use, learns towards greedy targets, regardless of exploratory actions, which can speed convergence to efficient routes, but may need thoughtful exploration management, i.e., like epsilon scheduling, to avoid suboptimal traps. So I really enjoyed this project. Thank you for listening. And I was happy to be able to show you parameter comparisons and evaluation matrices.